Assalamu alaikum. Welcome to W211. In today's class, we shall discuss some of the application of the circuit reduction techniques on some resistive circuits. We shall see how a complex resistive circuit can be simplified by applying the series and parallel circuit reduction techniques for resistances. Thereafter, we will see how delta to Y conversion and Y to delta conversions are actually performed in the course of uh, how delta to Y conversions are performed. So let us start. Let me draw a given circuit. Let me draw a circuit. So we have a resistance here. We are tasked to find out the R equivalent as seen by these two terminals A and this terminal number B. So as I mentioned in the last class that whenever we have to solve some circuit containing this type of network, then we should start with the resistances which are at the farmost end of the terminals. So thereafter we can actually have a strategy take the circuit back towards the terminals across which we are supposed to find out the resistance. As a startup thing, I shall first combine. I can see that this resistance as well as this resistance, both of these two resistances are in series. So I can simply have a series resistance that is equal to 3 kilo ohm for these two simple values, and this 3 kilo ohm, if I replace it with the 3 kilo ohm, then this 3 kilo ohms comes in parallel with this 6k, right? So my R equivalent 1 is equal to 3 kilo ohm, and my R equivalent 2 is 6 kilo ohm in parallel with this 3 kilo ohm, and this gives me 2 kilo ohm resistance value. So the new circuit that will emerge after this simple conversion is that we have this resistance, and we have this, and this one, then we have another resistance here. So we have this 10k, and this is the R equivalent 2. This is R equivalent 2. This is 6k. This is still let us put it afterwards. So this is 2 kilo ohm. So now if you see here, this resistance, this particular resistance and this resistance, they are in series, so they can be added together, and their series combination comes in parallel with the resistance of the 6 kilo ohm. So my third R equivalent is equal to 12 kilo ohm, and R equivalent number 4 is this 6k in parallel with this 12 kilo ohm resistance. And if I make a parallel combination of this thing, then this is 6 into 12 divided by 18, that is equal to 4 ohm. So that is 4 kilo ohm resistance. So now we have solved this particular circuit, and only we are left with this particular system network, right? So we forgot to draw a line here. This is 4k, this was 2k, this was 6k, this was 9k, and this was 4k, and this is 2 kilo ohm resistance, and we are slowly moving towards the solution towards this R equivalent circuit. Now if you see here, this 2k and this 4k comes in series. So we have R equivalent 5, that is equal to 6 kilo ohm resistance, and this 6 kilo ohm resistance comes in parallel with this particular 6 kilo ohm resistance, and therefore this R equivalent 6 is equal to this 6k in parallel with this 6k resistance, and this gives me a 3k ohm resistance. So if I redraw the circuit again, then I will get a resistance having this 3 kilo ohm here. We have this 9k here, this 4k here, and this 2k here, and this is the R equivalent. And now if we see here, the overall circuit can be emerged in the form of a more simplified circuit with this 2k here, with this 4k here, and then we have the sum of these two resistances, they will come in parallel with this 4k. So this is 12k. So the circuit will will look like this particular one. So this is 2K. So we have to find out what is the parallel resistance of these 4K and 12K. So this gives me R equivalent number 7, that is 12 cross 4 divided by 16, that is equal to 3 ohm, 3 kilo ohm, right? So we have 2 kilo ohm comes in series with this 3 kilo ohm, and as a result this R equivalent is equal to a 5 kilo ohm resistance. So this is the way to solve the circuits containing multiple resistive networks. So you see, this is all fun. You can always try modifying a given circuit by simply adding or dropping one resistance value or flipping the connections of some value. For instance, if we add a resistance here somewhere here, or if I make a resistance like this one, so this will create a new circuit, and that new circuit you should practice it at home to get more understanding and grip on finding the equivalent value of the resistance. However, there are some certain circuits in electrical engineering which are not that straightforward. So if you see, let me draw a circuit. Let me draw a circuit. In this particular circuit, it is not possible to find out if these values, if these resistances are in series or are in parallel, and such type of networks are known as the delta Y, or known as a bridge network. In a bridge network, you can see here, it is not possible to apply the rules of parallel resistance equivalence and series resistance equivalence. If we want to simply apply them together, it will straight away, it will not work. So to find out the equivalent resistance in such circuits, we have to apply some techniques that are known as delta to Y conversion and Y to delta conversion. And by mean I mean to say that we need to find out certain set of equations where we can actually transform this delta, which is forming as a result of this R1, R2 and R5, into some sort of a network where it can be represented in terms of this thing, or in terms of this thing. So I have to actually change this delta topology into a Y topology and vice versa, because there exists a Y as well. If you see here, there exists a Y as well, and that is if you consider only this branch. So this is actually a Y network. So without undergoing the delta Y conversion network, it is not possible to solve the circuits containing the bridge topology. So let us see how we can actually convert a delta network into a Y network and a Y network into delta network, and how we can thereafter we can retrofit the result into this particular bridge, and without changing the terminal characteristics we get the answer. So let us have, first of all, let's have a derivation of how these two networks are actually derived. Delta to Y equivalent circuit. Remember that the conversion of delta into Y or vice versa is not just the change of shape. We have to make sure that the terminal information is remain intact and that do not change the overall working or the topology of the given circuit, right? So let us see here. Let us say we have a delta network. This is RC, this is RB, this is RA, A, B, C, and then we have here. So let us call this one R1, let me call this R2, and let me call this R3. Now when I say that the terminal information cannot be altered if we want to convert a delta network into a Y network, what I mean to say is that if I connect, let us say I have connected some meter here. This is some measurement device. Let us say it's an avometer. It's an avometer, and I connect it across these two terminals A and B. Also, I connect another avometer here. This is an avometer, and I connect this the same with this Y as well. Now, if I connect these two things, then I should get the same value of the resistance as seen by this delta network and as seen in this Y network. So, what I mean to say here is that if I apply this meter to measure what is the total resistance here, then because of the operation of the avometer, a small current will flow and it will come into this junction number A, and it will divide into these two branches. Thereafter, consequently supplying the Kirchhoff's current law at this node, and then this current goes through this R of A, and then they combine at this node B and they go back to this avometer. So, consequently, the RAB for this delta network is actually equal to, so this RAB, we make it with this black pen, this RAB is actually equal to the series combination of this RB and RA. They are both in series. So, this there we have this series combination, right. So, we have this series combination here, and these series combination comes in parallel with this RC. So, we have RA plus RB in parallel with the resistance RC, right. So, we can write this as RC into RA plus RB divided by sum of all the resistance RA plus RB plus RC, right. However, in this particular case, for the case of this Y connected network, these two branches R1 and R2 are simply in series, because there is no path for the return of the current through this resistance R3. So, if we apply the same avometer across a Y network, then the equivalent resistance across the terminals number A and B, RAB, is equal to simply the sum of the resistance R1 plus R2, right. So, this is the basic concept of conversion of the network from a delta to a Y conversion, right. So, let me write it as that RAB is equal to RC into RA plus RB divided by, and that is equal to R1 plus R2. Remember that I have used the nomenclature R1, R2 and R3 for a Y connected network, and for a delta network we prefer to use the terms RA, RB and RC, and that is universal in most of the textbooks for linear circuit analysis course. So, we have to stick with them in order to have a uniformity across our learning and across our standard textbooks. Let us say this is equation number 1. Similarly, I can say that RBC is equal to, we have this RA, this RB plus RC divided by, okay, so we have the same thing, okay, that's okay, divided by the sum of all the resistance RA plus RB plus RC, and that is equal to R2 plus R3. Let me call this equation number 2. And then we have RCA, where we have RB and then RC plus R of A divided by RA plus RB plus RC, and that is equal to R3 plus R1. So, I have got the set of 3 equations for the terminal characteristics across the delta network and a Y network. Let us proceed further. Now, if I want to find out the value of the resistance R1, R2 and R3, then I have to do some mathematical manipulations here. So, first of all, let me subtract equation number 1 and equation number 3. That is what I want here is R1 plus R2 minus R3 minus R1, and that is equal to RC RB plus RC RA minus RB RC minus RB RA divided by RA plus RB plus RC. And in turn I will get, because this will cancel out with this one, so I will get R2 minus R3 is equal to, in here we have RC RB and this is also RB RC. So these two will cancel out. So I will get only RA RC minus RA RB divided by the sum of the resistance RA plus RB plus RC. Right. Let us say this is equation number 4. Right. If I add this equation number 4, if I add equation number 4 into equation number 2, right, now if I add this equation number 4 into this particular equation RBC, then what I get is this thing, that is R2 minus R3 plus R2 plus R3, and that is equal to RA RC minus RA RB plus RA RB plus RA RC divided by RA plus RB plus RC. So now if you see here, this will cancel out with this one, and consequently what we will get is 2 times R2 is equal to 2 times R of A RC, because this will also cancel out, RA RB will cancel out. So we have RA RC left divided by RA plus RB plus RC. So now this will cancel out as well. So R2 consequently is equal to RA RC divided by RA plus RB plus RC. And on the similar pattern we can find out the equivalence for the resistance R1 and R3 as well. So let me write them as well. So this is R2, consequently we have R1, that is equal to RB RC divided by RA plus RB plus RC, and we have R3, that is equal to RA RB divided by the sum of the all the resistances. So this is the expression to convert, this final is the expression to convert a Y network, a delta network, delta to Y, right. So we have for this one, this is delta to Y conversion, and on the similar manipulations across these three equations, we can also derive how we can actually convert a Y network into a delta network. For that I will only write the equations, you can always derive it yourself using your basic knowledge of mathematics and circuit analysis. So the final expressions for the resistance RA, that is equal to R1 R2 plus R2 R3 plus R3 R1 divided by the resistance R1. Similarly for RB we have R1 R2, the above this expression remains the same, divided by the resistance R2, then we have RC, that is equal to R1 R2 R3 R1 divided by resistance R. This as a whole, this provides me expression for a Y connected into a delta connection, right. This is how we can actually convert this delta into Y and Y into delta. Now if you want to know, because sometimes it is always difficult to remember these by heart, then there is a small trick as well. Let me tell you that secret as well, right. So let us say we have let me draw, let us say this is RC, this is RA, and this is RB, this is R1, this is R2, and this is R3. Now, if you see here that RA, the expression of RA contains the sum of, or RA is I can simply write as RA is equal to R1 R2 plus R2 R3 plus R3 R1 divided by the resistance which is opposite to this RA. If you see in from this particular section, from this particular section there is only one resistance which is opposite to this RA. In other words, it will be divided by that particular value of the resistance, or that resistance which has no direct connection with this RA. So, if you see, this R2 has a direct connection with this R2, there we have this direct connection, and also with this R3 we have a direct connection of this R of A. So, we can write this that we have to divide it by this resistance R1. So, this is the first thing. If you want to convert any resistance, you just need to divide it, and this is for converting this Y network into a delta network. Conversely, if you want to find out what can be the value of the resistance R1 here, what is the value of the resistance R1 here? So, the value of the R1 resistance is equal to, we will have to multiply it by those two resistances which have a direct connection with this resistance R1. So, if you can see here, this RC has a direct connection at this node, this RB has a direct connection here. So, this becomes equal to RB RC divided by the sum of the resistance RA plus RB plus RC. So, these are some of the tiny tricks that always help a student in solving a circuit in a more faster way in during the examination and during their studies. Let us apply these delta Y transformations on a simple circuit and see how we can solve electrical circuits using these methods. So, I will draw a simple circuit as always. I always draw simple circuits. So, we need to find out what is the current supplied by this 40-volt source, and what is consequently what is the power which is supplied by the source which is connected here. So, for that we need to convert some of the triangles. There are two triangles here. We need to convert them, either the top delta or the bottom delta, into an equivalent Y network, and then we will retrofit that delta network into this bridge circuit, and that will make the things super easy for us. Let us apply those expressions on this circuit to find out what is the total power supplied by this 40-volt source. Let us first target what delta network we want to convert into Y. So, I want to convert this top delta network into an equivalent Y network. So, let me draw it here. So, we have this 100 here, this is 125, this is 25, and inside I want to draw this network, and that is R1, this is R2, and this is R3. So, R1 we calculated and we derived the expression for R1 to be equal to RB RC divided by RA plus RB plus RC. Now, if you see this R1, this we don't know what is this RA, RB and RC, but we do know that the resistances having the direct connection with this R1 are to be multiplied and put in the numerator. So, that is equal to 100 into 125 divided by 100 plus 25 plus 125, and that is equal to 50 ohm. Similarly, R2 is equal to, R2 will be multiplying this 125 with this 25 and then divided it by the sum of these three resistances, 100 plus 25 plus 125, and this gives me 12.5 ohm resistance, and for R3 the equivalent resistance is equal to 10 ohm using the expression that we have derived so far, right. So R3 will be multiplied by the 100 ohm and this 25 ohm resistance value. Now that we have the values of R1, R2 and R3 available, we can replace this triangle which is shown in this highlighted yellow highlighted color. We will replace it with the equivalent Y network, and then we will solve the circuit. So let me modify the circuit. Now the circuit after the modifications becomes equal to, this is the Y network. So here we have R1 that is equal to 50 ohm. This is R2, so R2 is equal to 12.5 ohm, and then we have 10 ohm here, and thereafter we have this resistance of 40 ohm and another resistance of 37.5 ohm, and this is actually connected in this fashion. Now if you see, this has actually simplified the circuit a lot. Now we know from very straight away we can say that this resistance and this resistance are in series. Similarly, we have this 12.5 ohm resistance and this 37.5 ohm resistance are in series, and the connection of these two resistances comes in parallel with each other. So if I solve this particular circuit, then we have R equivalent is equal to 55, which comes by the summation of these two resistance values, right. So this 5 ohm and this 50 ohm, they are combined together in this 55 ohm value, plus then we have this 37.5 and this 12.5 making a sum of equal to 50 ohm. This 50 ohm resistance with this 50 ohm resistance divided by 100, this gives me 25. So 55 plus 25, this gives me an equivalent resistance of 80 ohm resistance. So now you can see that this whole bridge network, which was supposedly a very messed up type of a circuit, a very difficult circuit, it has been solved in terms of a very simple circuit of a value equal to 80 ohm, and that too with a voltage source of 40 ohm, 40 volt. So now the equivalent circuit that I may draw is this one. So we have this 40 volt source here, and this is feeding to an equivalent resistance R equivalent that is equal to 80 ohm resistance. Now the current I is equal to V over R equivalent, and that is equal to 0.5 ampere, and of course it will flow in this particular direction. So the power is equal to minus 20 watt, which says that this source is actually transmitting the power, or it is supplying the power to the resistive element which is connected here. So this is how the simple circuit reduction techniques are very helpful in finding out the power and in finding out different other parameters in a given circuit. So far we have studied all the basic techniques to solve a given circuit. In the next class, we shall start some of the more advanced techniques which are known as the mesh current analysis method and the nodal analysis method, and that will help us in solving even more complex circuit that we have not discussed so far. So till then, take care. Allah Hafiz.